Alright class, today we're going to start on balancing chemical reactions and phases. So we're going to start this lesson. Take your time, you could pause this video whenever you want, but just know that you could always pause to try out any example questions because I want to go a bit fast sometimes, okay? So, we're going to go over the big idea. There are various strategies involved in balancing chemical reactions, and you need to balance a chemical reaction for calculation purposes because it's going to be very important when we jump into stoichiometry. Now, for some of you, you might have remembered that you balanced in Science 10, but this is a quick refresher, okay? So, what are some evidence that a chemical reaction has occurred? Well, one of the first evidences that we always have is that there is energy change. Now, how is energy changed? Well, energy is usually changed because you're going to see some release or absorption of heat. And if there's a release of heat, there's usually some release of light as well, and you might know this as a combustion reaction. Another evidence, precipitation is formed. Now, what does precipitation mean? Precipitation means that a solid forms. Another evidence is that bubbles form, but we know that this means that boiling is not a chemical reaction. Because when you boil, you're actually just increasing the size of the gas particles. So not from boiling. The last one that usually is an evidence is color change. Now, this is pretty straightforward. If there's a color change, that means there must be something that has changed in that chemical. Now, if you notice that if my writing is kind of messy or if my writing is a bit small, I'll use a bigger font size for this next one to see if it's better. But we want to go into some conservation laws. There are conservation laws in science, especially in chemistry, that allows us to balance. So we gotta make sure that when we talk about conservation laws, we usually talk about it in terms of in an isolated system. Now, what is an isolated system? Well, first of all, we gotta talk about what systems are. Systems are what you are gonna be studying. So a system is what you're going to be studying. Now, it could be a beaker, it could be a container. Now, what we mean by isolated? Isolated means that it cannot exchange with the outside surroundings. So an open system is where you could have particles enter, you could have particles leave. Not only that, but energy can also come in and leave. A closed system is like, for example, you put a lid on a container. Now there's going to be no more chemicals entering or leaving, but that container may still allow energy to be transferred. That's how, for example, you boil something in a pot. Because when you close the lid, you're trying to stop the thing from escaping, but you're still increasing energy of that food you're making. Isolate system is where you, for example, have a vacuum seal, a thermos, something that doesn't allow energy to also leave or enter. So that's what we're talking about. In an isolated system, reactions will always follow. Reactions will follow. Okay. What will they follow? Well, the first one is, you might know this, conservation of mass. So conservation of mass means that mass will not change in the reaction. Number two, there will be conservation of electrical charge. That means what you have at the start of the chemical reaction and the end of the chemical reaction, the charge will not change. So conservation of electrical charge. The third one is one you probably are pretty familiar with. Conservation of energy. Conservation of energy means that energy cannot be created or destroyed. It can only be transformed. And the last one, the one we're going to use to help us balance, is conservation of atoms. And this is the one we're going to use to help us balance chemical equations. So it's the one where we want to make sure that atoms can total number of atoms from start to finish will not change. From start to finish will not change. So, this is what's going to help us balance. Okay? Now, we need to know some important terms before we progress, because if I say these terms, you need to know what they mean. One of the first terms you're going to need to know for this lesson is you want to know what a reactant is. A reactant is our starting chemicals. Okay? Well, if we have starting chemicals, we must have the final chemicals, the resulting chemicals. And that's called our product. Our product is our resulting chemicals. What is going to be created after this reaction occurs? We also have a term that we've used before, and that's called coefficients. Coefficients are the numbers you use to help you balance. It's like algebra. So it's the numbers that represent the number of each formula. So we have these different terms that I'm going to use quite a lot in this lesson. Now, if you will scroll down, or in this case, if you will flip the page, why? Why must we have closed system? Well, we talked about this earlier. We do not want chemicals to enter or escape your reaction. Which means that, what that means is your number of starting chemicals equals the number of resulting chemicals. This is what's going to help us balance. Now, what are some strategies to balancing chemical equations? Now, these are strategies that I've been using for a long time. Now, don't feel like you need to stick to these strategies, because sometimes you could develop your own strategies and they might work for you. But if not, then I would say try these strategies out and see if they work for you, because they work for me. So what do you want to do? What's the first step you always want to do to balance chemical equations? Well, the first step I usually do is I always want to balance what appears once on both sides. Now, what does that mean? What that means is usually these are chemicals that only appear in one chemical on each side. These usually are the metals. Usually they are metals. Now, if there are no metals, they're usually not oxygen or hydrogen. Okay? Because we usually want to balance these two last. So you always want to balance these two chemicals. Usually you want to balance them last, because they're going to appear usually more than once. Now, what's step 2? Well, you just balance your, for example, your metal. You now want to balance what is attached to that metal. What is attached to what you balance in step 1? Okay, so you want to balance what you just balanced in step 1. So that's our next step. Okay. So this could be, for example, if you have NaCl, you're going to be balancing, you balance the Na in the first case, so sodium in first case, and now you're going to balance Cl in the second step. Okay, what's step 3? Step 3 is going to be repeat step 1 and 2 with a new chemical. And you want to keep doing this until everything is balanced. And this works for pretty much 90% of all chemicals until you run across some other more complicated ones. But in our course, we usually do not run into those. Some strategies you want to make sure you have is, for example, balance polyatomics as one group. So balance polyatomic ions as one group. Okay, so do not break apart. If it's SO4, if it's sulfate, do not break apart and balance the sulfur by itself and the oxygen by itself. Balance the SO4 together. Okay, here's another strategy I usually have. If it is what we call a reaction that involves water as an ionic compound, if it is in, I don't put an apostrophe, ionic reaction, write H2O as HOH. The reason why you want to do this is because H2O, water, is actually, when these are reaction, coming from a hydrogen, in this case usually an acid, and an OH from a base. And using that, you're going to see OH from one side, which is a polyatomic ion, but you're going to end up not seeing OH on the other side if you just write it as H2O. Instead, if you write it as HOH, you can actually see that this is an OH group. Okay. Now, I have this rule that some of my former students might remember, but if you do remember this, great. If not, it's not really needed. I call it a double, odd, even rule. Okay, and I'll tell you what this means. An example of this is such as, for example, if you have, let's say, for example, you have a number such as you have, I don't know, 7 oxygens on one side, okay, and then you have 8 oxygens on the other. What do you do to balance these? Do you multiply the 7 by 8 over 7? You could. The other option I usually ask students to do is, if you run into an odd-even situation, you want to double both and everything that you already balanced. So in this case, you want to double everything, times it by 2. And when you do that, you're going to make your life a lot easier. I'll show you examples of that in a bit when you get into examples. Okay, so just remember double, odd, even rule. Now this is what you want to make sure you have so far. This is something that you should have already actually learned in Science 10. Now here are some new stuff that you should have, and if you need more room, your next page of your notes should have more room. What you want to have now is what we call, you want to add some states. So step 4, you want to add states of matter. Okay. So what does that mean? Well, this means your solid, liquids, and gases. So what you do to represent states of matter is right below the chemical formula. Especially, for example, if you have water, you want to put as a little subscript L in brackets, and that states that this water is a liquid. Likewise, you have solid is going to be S. Again, liquid is going to be L. And gases are going to be G. But there's actually a fourth state that you need to write, and this is called aqueous. Aqueous is, first of all, it's AQ, but what aqueous is really any solution, any ionic solute that is dissolved in water, and we call it aqueous. So examples of things that are aqueous are, for example, NaCl can be aqueous. Or, for example, KOH can be aqueous. Aqueous can only happen when it's ionic. So make sure you note that, only for ionic. Okay? If it's not an ionic, which is a metal or non-metal, you cannot make it aqueous. So solid, liquid, and gases. Now, how do you know if something's a solid, a liquid, or a gas? Well, it's really common sense. If you write, for example, gold, gold is a solid. If you write, for example, oxygen gas, well, it has the name gas. In that case, it must be a gaseous state. So let's practice this, okay? So we got to talk about practice now, right? So let's see what we have here when we go through situations like this, okay? And I might add a few more examples. So let's practice some of these questions. So let's look at this one. Here we have H2S, which is, in this case, hydrosulfuric acid, lead 2 chloride will react together to form lead 2 sulfide and hydrochloric acid. So what should we balance first? Well, what we want to do here is we want to balance, in this case, step 1. Step 1 states that you want to balance what appears once on both sides, and this is usually the metal. So you want to balance that first. So in this case, you want to balance Pb first, or lead. Well, in this case, what do you know is where your lead? Your lead has 1 on this side, and you have 1 on the other side. So in this case, they're balanced. Well, step 2. Step 2 is where you want to balance what is attached to what you balance in step 1. So in this case, if you look at our lead on our reactant side, the lead has attached to chlorine. We have 2 chlorines here, but we don't have 1 here. So we got to put a coefficient of 2 in front of this to balance out the chlorines. So the chlorines are now balanced. Okay, let's try and balance and repeat again step 1, step 2. So in this case, we have no more metals, but in this case, because hydrogen is at the front of a chemical reaction, we treat it as if it is a metal. Well, in this case, we have 2 hydrogens here. Initially, if we didn't have this 2 here, this hydrogen would have been 1. But this 2 means we also have 2 hydrogens here, so the hydrogens are balanced. Our last step, what's attached to hydrogen? It's sulfur. There's 1 sulfur here, and there's 1 sulfur here, so it's balanced. So this is now a fully balanced equation. If you want to pause the video and try the next 2, you can, but I'm going to move on to the next 2. In this case, let's look at this one. In this question, we have what we used to call a combustion reaction. A combustion reaction is where you have a hydrocarbon, a compound that contains carbon hydrogen, reacting with oxygen gas. Will give you carbon dioxide and water. Now, some of you might have just noticed that I didn't write the states. This is where you could write the states. In this case, because all these are ionic compounds, you could write them as aqueous. It's a little messy, but aqueous. Aqueous and aqueous. Now, in Chemistry 12, you're going to learn that this reaction actually will not take place unless on the product side you actually form one of these as a solid. But that's a Chemistry 12 topic. For now, if you see an ionic compound, you could put that as aqueous. So let's try balancing out the second question. So the second question, because it's what we call a combustion reaction, there's no metals involved. But my rule is you always want to balance oxygen and hydrogen last. As you can see, you have 2 oxygens on the product side, and it makes it really difficult to balance them if you balance them first. So let's balance the carbons first. Right here, you see that you have 3 carbons here, but only 1 here. So you want to put a 3 in front of this to balance the carbon. Okay. Now you see that this carbon is attached to the hydrogen. Well, if this is attached to the hydrogen, we want to balance the hydrogen next. We have, in this case, we see that we have 8 hydrogens here and 2 here. So we want to make sure we turn this product side hydrogen into 8. So we put a 4, because 4 times 2 is 8. Our last step now, balance the oxygens. We see that we have 2 oxygens here, but we have 3 times 2, which is 6 oxygens here, and 4 times 1, which is 4. So we have 10 oxygens total. In this case, we need to make this 10 as well, so we put a 5 in front of the reactant side, oxygen gas. Now we want to add some states. This C3H8 is called propane. As you know, propane is used in barbecues, and it's a gas. Oxygen gas is a gas. Carbon dioxide is what you breathe out. That's a gas. And water. Water is a liquid. So you want to put an L there. My L's are loopy. Now if you want to pause the video again to practice the last one, you may, but we're going to do the last one together. So this last one here is H3PO4 plus NaOH gives you Na3PO4 plus H2O. So this is actually what we call an acid-base neutralization question. So you have a hydrogen at the start which acts in the metal, that's an acid. You have an OH group with a sodium, that's a base. And it always forms what we call salt and water. So let's try balancing this. But as you see, you have an OH group, that's a polyatomic ion. So your first step when you see this case is to write water differently. You want to write water as H, OH. And that's going to help you balance this question a lot easier. So let's start out. So you see that you have two metals here. Hydrogen also acts as a metal, but let's start by balancing the sodium. You have one sodium here, you have 3 sodium here, so you should put a 3 in front of this. Well, what's attached to the sodium here? It's OH. Ah, this is where the OH comes into play. You have, as you can see, 3 OH groups. So because of that, you want to write 3 OH groups here. So because there's only one, you need to put a 3 in front of this as well. Well, let's look at this one. You have 3 hydrogens here. Over here, you have 3 hydrogens. That's balanced now. And if you look at it again, you have one PO4 group because that phosphate is a polyatomic ion. I want to make sure I keep them together. And over here, you have one phosphate as well. So this means that you now are fully balanced. But you need to write the states. So the states in this case, again, are aqueous, 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 but water. Water is a liquid. It is a pure substance. It must be a liquid because it is majority covalently bonded, not ionic. Now this is your homework here, okay? Now this might seem like a lot of homework, and I'm actually going to just take a look at my textbook to make sure it's not too much, because I may edit the amount of homework you have. And let's take a look at this. So, page 110, number 7 to 55 odd. No, this is not a lot of homework, so I want you to complete this homework, and if you have any questions, please attend my office hours. But there's one more question I want to work with you. This is a little bonus question. I'm going to take this second question and modify it slightly. I'm just going to add 1 extra carbon and 2 extra hydrogens to this reaction. I want to see what happens there, okay? So I'm going to write it right here. So we're going to have C4H10 plus still oxygen gas gives you still carbon dioxide and still water. So let's see what happens here. And this is where the double odd even rules comes in. So here we see we have 4 carbons and only 1 carbon on the product side, so we want to put a 4 in front of this. And over here we see that we have 10 hydrogens but only 2 here, so we want to put a 5 in front of this. Okay, let's count the oxygens now. We have 4 times 2, that is 8 oxygens, plus 5 times 1, that's 5 here. So 8 plus 5, we have 13 oxygens on the right side, but we have 2 on the left side. What do? We have an odd number on the left side, and an even number on the left side, and an odd number on the right side. Some of you could say, I could just multiply by 13 over 2. That works, and then you want to get rid of the fraction. But my rule works too. Because you already balanced 3 of these numbers, right here, 1, 2, 3, what you just got to do is you want to double every single number you balance except for the one you haven't balanced yet, which is the oxygen gas. So if I rewrite this as 2C4H10 plus still the O2 I haven't balanced will give you 8CO2 plus 10H2O. And now, as you see here, you now can make this balanceable now. The carbons are still balanced because you have 8 carbons here and 8 carbons here. The hydrogen is still balanced. You have 20 hydrogens here, you have 20 hydrogens here. But this now makes it so that your oxygens can now be balanced. Because you have, in this case, if I write it out as a small number, 16 oxygens here plus 10. You have, in total, 26 oxygens. So what number times 2 gives you 26 oxygens? 13. And that's the double odd even rule. Now, if you want to practice this, this usually works really well when you deal with what we call hydrocarbons, in which the hydrogen is a number that is what we call, when you divide in half, will be an odd number. So in this case, when we dealt with it here, we had 10 hydrogens, but we end up with a 2 here. So if you divide it and it gives you an odd number, it'll be 5, it will work. If it's 12, though, it will not work, actually. Okay, so I want you to practice this homework, and if you have any questions, please send me a message through the Microsoft Forums, and I'll answer it to you during the office hours. I want you to make sure that you stay safe and healthy, and I'll see you soon.